call is now being recorded.
Okay. Last time we have seen the detectors. Just take a look, quick review on the detectors. What is meant by detector and what are the properties of its classification. Just mute your mic. So there are different types of detector can be classified as a concentration detector, where is the concentration of the analyte is determined. Second is the mass detector, where the total mass of the analyte in the carrier gas is determined. Then universal detector, which detects all the compounds. An example of that detector is PCD. Then selective detectors, as name suggests, selective means selectively detect that particular compound. That's why it is called selective detectors. For example, if you want to detect halogen sample, then you need ECD type of detector for the instrument. So one of the most important detectors generally used in the GCMS is the flame ionization detector. In short, it is called FID. Okay. So this detector is very helpful. It is mass sensitive instrument. So it determines the mass of the analyte in the GC sample. So this is the history that we have seen in the last lecture. It is invented by the two different groups. One is the from Australia and New Zealand, and second from the South Africa. So this is the operating principle of the ionization detector. As name suggests, flame ionization detector means there will be flame ions formation, and that ion will be detected by the detector. So it is based on the detection of ion formed during the combustion. Combustion means total burn of the organic compound in a hydrogen flame. So it is called combustion. So the generation of these ions is proportional, means so if concentration is more, the formation of the ion is more. So it is directly proportional. If concentration is low, the formation of ion is also low. Okay. So this is the diagram of the FID. Already we have seen there is a flame, there is an inlet for the air, hydrogen, and this blue line, sorry, this red line is for the column input, where the sample will come inside this flame. And this is the detector, and this is the exhaust. When after detection is there, all the samples will be thrown out from this end. So it is called exhaust. Then we have seen the two video. This is the one, and this is the second video. Although we have seen this, so I am not going to discuss that video. These are the advantage. Remember this advantage. One is the its cost. Cost is very low. It is, we can say that it is relatively inexpensive. Okay, low maintenance and rugged construction. So you can easily handle these detectors. Still, it has some disadvantage. There are two main disadvantages for this. It cannot determine the inorganic substance. For example, if you want to measure the NaCl compound, you cannot use this detector for detection of the NaCl compound. So all inorganic compounds cannot be detected by this detector. And second major drawback of this instrument is detector is you cannot detect CO and CO2 gases. With some modification, you can detect, but still it has some limitation. Modification is the use of methanizer. You have to install this methanizer in the detector. This methanizer is nothing but the bed of nickel catalyst. But this nickel catalyst get poisoned by the gases. So this is not good for the determination of CO or CO2. This is the second determination. And third is the it oxidizes all the compounds. That's why you cannot use very frequently. Now our next part is very important. This is the instrumentation of the GCMS, and the circle, pink color circle. Now we are going to see, and it is called transfer line. Okay, transfer line, or it is also called interface, and this is very important part, an important device of the this GCMS, because it connect both GC and MS. Okay, if there is no this point, then you cannot connect these two instruments. And this is very important because, as we know, GC operate or works under high pressure, whereas MS operates at low pressure or high vacuum. So we need such a device which can combine these two instruments. And this is called transfer line of interference. Now let's see why. Why it is important. As I said, the carrier gas that comes out of GC column is pressurized gas, because GC work under high pressure. So automatically the carrier gas will have high pressures. For example, this flow is about ml per minute if capillary column is used, or 150 ml per minute if it is packed column. Okay, so in GC we use high pressure. But in contrast, the mass spectrometer works under high vacuum, that is low pressure. Okay, pressure and vacuum is inversely proportional. Okay, so this mass works under high vacuum. For example, it works at 10 to minus 4 Pascal or 10 to minus 6 torr. So to combine this, we have to adjust the pressure of the carrier gas. And to adjust, we need such a unit that is called interference for instrumentation of good working of the instrumentation. And this can be done by using the pumping power. If you have pumping power, means which will pump out the gas or pressure, it's called pumping power. Okay, this will require at the interface region in order to provide a compatible condition for the coupling. Now let's see the interface. आवाज व्यवस्थित येतोय ना? सांगा मला थोडं येतोय.
हो सर येतोय. हो सर. हो सर येतोय.
Okay. Now let's discuss the interface. Okay, there will be a question on 5 to 10 mark on this point, because this is the main part. As said, it connect two instruments. So understand this point in well details. Now let's see interface. Always remember, the main task of the detector is the differentiator, means to make the difference. So, and this difference can be done by the interface by minimizing the mass flow rate of the carrier glass into the ion source while maximum the amount of sample transfer. So what is the meaning of this line? So in GC, you have amount of carrier gas. For example, let's say helium. We are using helium. So its amount will be high, whereas the amount of analyte is low. This is the condition in the GC. But in mass, we require a high amount of the analyte as compared to the amount of helium. So we have to take out the helium from the sample or carrier flow, and this can be done by the interference. So there are three types of interference in GCMS. First one is the molecular diffusion enrichment device. Second is the molecular jet enrichment device, and third is the selective membrane devices. So these are the three devices you can use for the GCMS. Now let's see one by one. Before that, let's see how it works. This interference, how it works. It works either two way. Okay. Remember that in both the way there is one membrane. Okay, a barrier, we can say that. Barrier means which obstacle the flow of the gas. Or membrane the same way, membrane which obstacle the flow of the one of the component. This is called membrane. So it will work either pass the sample through a barrier membrane to the mass spectrometer. Means it only pass the analyte. It will not pass the helium gas. So this is the first way. And second way is that it passes the carrier gas through a barrier. Means it will take out the helium out of the analyte and it will be pumped away. Okay? So these are the two way this interference works. Now let's say first interference, molecular effusion. So this is the first interface used by the two scientists. One name of scientist is Watson and Beeman. They used it for JCMS in 1960 around. So this is the diagram they given. Let's see the diagram. This is the more complicated. We will next slide. We will see the simple diagram for the molecular effusion, so you can understand the what is the meaning of molecular effusion. Now let's see this direction. Right side is the from GC means the carrier gas will enter from this end. Okay, and this is the ion source means after this point the ionolite will enter into the MS. Okay, now look at this diagram. There is a one tube. This is the outer tube, and there is a one inside tube. Okay, here you can see that this is the pump. So here you can take out the pressure from by using pump, vacuum pump. We can say that. Okay, and it is called evacuation chamber. So this outer is called as the evacuation chamber. Now, inside of evacuation chamber, there is a one tube. So this is the one tube. Okay, and this tube is called porous glass tube. Okay, porous glass tube means what? It has small size of holes from which helium can be thrown out or pass out. Porous means it has small size of holes. Now, when your carrier gas will go through this line, it will come here. And since this glass has pores, so helium only come out and only analyte will pass through the this line. And there is a vacuum, so automatically all the helium will be taken away through this end. Okay, so this is the working of the molecular diffusion. Now let's see simple diagram so you can easily understand how it works. So this is the simple diagram we can explain for the molecular diffusion. Now there are two important keywords. One is the analyte molecule. It is represented by the red dots. And second dot is the black one. It is represented by it is carrier gas. Okay. So this point is the evacuation chamber. This whole big block is called evacuation chamber. This here is the pump. Vacuum pump will be here. Okay. Carrier gas will enter from this end, and through this end it will enter into the mass spectrometer. Okay. This inside of this evacuation chamber is the glass, which is called sintered glass tube. Okay, and you can see that there are small gaps. Okay, one is here, so this second, this three. So there are number of these pores. Pores means small size of holes. Okay, both the side you can see that there are pores, and these through these pores the helium will go out, will be taken away from this end. So only your analyte sample will pass through this sintered glass tube, and maximum amount of the helium will be taken away by this way. So what will happen? Suppose before the entering, amount of helium will be high and amount of analyte is low. Okay, but while passing through this end, the amount of analyte will be more and amount of helium will be less, and this is called as enrichment. Okay, enrichment means uh, growth of the increasing amount of the analyte. Okay, so amount of analyte here and amount of analyte here will be different. At this end, amount of analyte will be maximum as compared to this end, and it is called enrichment. And through this molecular effusion, we can achieve enrichment up to 5 to 6 fold. Okay. Now, what is mean by 5 to 6 fold? Suppose you have here, before entering this interface, suppose you have 5 analyte per 10 uh, helium ion. Okay, let's just simple example: 5 analyte and 10 helium. But this end you will have 9 analyte and 10 helium. So amount of analyte will be increased. That is called enrichment. When this helium comes out this through pores, it will be taken by this pump. Because pump will pump will do? It will suck the all the helium and will exhaust through the chamber. So this is the working of molecular diffusion. Now let's see, there are different types of material we can use for this system. This is the first one. This tube is called the sintered glass tube. Instead of sintered glass tube, you can use various type of tubes. One is the thin-walled Teflon tubes, which proposed by the scientist Lipinski. A second tube is the porous silver membrane, which is used by the Cree scientist for the GCMS. Or you can also use stainless steel tube. Okay, here stainless steel tube. It is by Cruiser and McCloskey. So these are the three tubes you can use. But remember, these three tubes have little bit disadvantage or problem. So what is the disadvantage of these three tubes? You cannot use polar compound with using this membrane or tube. If you use this tube and you are using polar compound, there will be some modification you have to do with these tubes. So what is that modification? That word is salinizing agent. Means you have to put the coating on these tubes. And this process is called as salinizing agent. Then you can use this tube for the polar compound. Otherwise, you cannot use the simple one. But scientist Marche developed one new tube, and it is called glass-free molecular diffusion. And there is no need of this salinizing agent for this tube. It can be work very well for the polar compound. So these are the tubes you can use as an interface in the molecular diffusion. Okay, so this is all about the molecular diffusion. Now second type is the molecular jet. Okay, so what is meaning of jet? Like it is a pressure gun, we can say that. So molecular jet means it will uh, send the molecule with high speed. Jet means we throw out the molecule with high speed. So these are the earlier diagram used by the scientists to represent the molecular jet. Now let's see one by one. So this is the first one, which has the only single molecular jet, and this is the second diagram which has double molecular jet. You can see that this is the only one here. This is the first and this is the second. So it is called conjugative molecular jet. With this second diagram or second molecular jet, we can achieve maximum enrichment. Okay, we can also achieve this enrichment, but as compared to this second one is better one. Okay, now take the simple look of this diagram. So this is the simple look of the jet molecular jet or jet separator. Here you can see that one end from GC means sample will come inside along with the carrier gas, and second this one is analyte will go into the mass spectrum, and this is called center part is called the evacuation chamber, means where the analyte carrier gas will be taken away. Now let's see the working of this jet separator. Now we know the weight of the helium will be lesser than the weight of the analyte. Since all the organic compounds have high molecular weight, so its weight will be higher than the helium gas. So when you pass this and carrier gas along with the analyte through this end, here you can see that this end of the inlet is very small. Okay, it is called nozzle. Okay, so when you pass this dairy gas, it come out very fastly and will get expand into the evacuation chamber. So here you can see that all the gases coming out this nozzle get expand. So lighter helium will be expand more rapidly as compared to the heavier analyte. So you can see that this helium is expand or go away as compared to the this analyte. So only this through this end only analyte will enter to the this end. This is the second end. Okay, and remaining helium will go outside. So movement of the analyte is more than movement of the helium. So what happens? Only analyte goes through this line and helium goes side. When helium goes side through this line, it will be evacuated or will be pumped out by using vacuum pump. So this way you can removing the helium from the analyte in carrier gas and making sample more rich. Here you can see that in inlet you can see there are a total 6 dots for the helium and only 3 dots for the analyte. But this end you can see that only analyte is there, helium is taken away by the vacuum pump. So this process is called the diffusion, and this can be done by using the Z separator. Okay. Now third one is the perm selective membrane. And as the name suggests, there will be membrane. Everyone knows the what is meant by membrane. Okay. Selective. So what is meant by selective? Means that membrane will work with only selective material or selective component or selective analyte. Okay. Now let's see how it works. There is one word you have to remember in this point. It is called permeability. Okay. So what is meant by permeability? Let's see. So here definition is given. Permeability is nothing but it is solubility into rate of diffusion. So solubility into rate of diffusion is called as the permeability. Okay. Huh? Now this selective perm selective membrane is working or is based on the large differences in permeability of between most organic molecules and the carrier gas. Okay, so you have to remember that if there is no difference in the permeability, then this device will not work. Okay, so there should be large difference in the permeability of the helium and organic compound. Otherwise, it will not work. Now, see in diagram. So this is the inlet. Carrier gas along with the analyte will enter through this end. Okay, so this is the evacuation chamber. Okay, this bottom end outlet is called uh, evacuated. And here you can use the vacuum pump. So all the helium will pass out, and this end where the analyte will enter into the mass spectrometer. That is MS. Okay, and this black line is called the membrane. Okay, now this membrane. Sorry. So this membrane have uh, now when the samples from the GC inlet comes, there will be helium and the organic compound or analyte. Now this membrane have typical permeability for the organic compound. Helium will not pass or will not get soluble or will not diffusion through the membrane. Okay, so what will happen? So only analyte or organic vapor will pass through this membrane because this organic compound has good permeability as compared to the helium. And this membrane will allow only analyte molecule to pass through it. And helium molecules will come here and will be taken away by the vacuum pump. Okay, so this way you can do the enrichment of the sample by using membrane. Here you can see that in this case the amount of helium is larger as compared to the analyte, but This end, where the sample enters into the mass, has more concentration of the analyte, and we required more concentration for the MS. So this is called constitutive membrane. Now this membrane is made of the one thing compound. It is called dimethyl silicon rubber. This membrane is made of dimethyl silicon rubber, which has a thickness between 0.025 to 0.04 mm. So this is the size of the this membrane. Okay. And by using this membrane, you can do the enrichment up to 10 to 20 fold. So you can increase concentration of the analyte by 10 to 20 fold. So that's why it is called pump-selective membrane device. Now next part is the ionization source. Now this part is done. Transfer line or interface. Now this pink part is very important in the mass spectrometry. It is called ionization source. So ionization source means what? Where the formation of ion will take place. It is called ionization of source. Now let's see in details. So ionization source is nothing but the component or the device which convert the component of sample into ions by bombardment of electrons or ions or molecules. Means what? When your sample enters into the ionization source, it will be bombarded with the electrons. It will be heated by the electrons. So there will be collision. When collision takes place, there is a formation of ion. So your component or your analyte converted it into the ion. That's why it is called ionization source. So there are two types of ionization source generally used in the mass spectrometer. First one is the electron impact ionization, and second is the chemical ionization. Okay. Now we have to see the what is meant by electron impact ionization and how it works. Okay, generally these two ionization sources are used in the GCM or MS. Now let's see the electron impact ionization source. So as name suggests, in name you can see that the word electron impact. So what it mean? That there will be use of electron to form the formation of the ion. Okay. So as its name implies or suggests, electron collide with the gaseous molecule to form the ion. So remember this. Okay. So there will be electron and there will be gas and there will be collision between electrons and gaseous molecule and formation of the ion. Because MS works on the ion. Okay, mass to charge ratio as we know. So there must be a formation of ion, and this can be done by the EI, that is electron impact ionization. Okay, so here in this system you are producing the electron, making it collision with the gaseous molecule, and there is a formation of the ion. Now let's see how it works. See the diagram. In this case, you can see that this is the filament, and it is tungsten or other filament you can use. Okay, and this tungsten filament is connected to the high voltage current. So this is the voltage current. It is attached to this filament. Okay, this end is the GC flow. Means sample will come after passing through interference. It will enter into the ionization source. So this is the inlet. This is the molecular analyte. This is the outlet, okay, to the mass analyzer. The sample will go to the mass analyzer from this end. Here you can say that this is the negative side, this is the positive anode. Okay, so when electron is generated from here, it will pass through this path towards this. So when it reach here, the current will be measured, or electron will be measured. How much it passed through the this line. Now see the work. So remember 3 points. First one is the formation of the electron. See, your electrons will be formed, will be having high energy. The energy of this electron is around 70 electron volt. Okay, and this much energy required in mass spectrometry. So The first part is the formation of the electron. Second is the entrance of the molecules. When these molecules and electron from this side comes to here or collide, there will be formation of the ion. So formation of ion will be take place in this region, and that ion will be taken towards mass analyzer. So this is the working of the electron impact ionization. See, so here we can see that electron which having 70 electron volts are produced by the heated filament. So this is the heated filament and accelerated to the anode. So this is the anode. Okay. So formation of electron takes place here and accelerated to this end. It is called anode. So gases compound from GC flow. So gases compound means which has a organic compound analyte will enter to this end and there will be a collision. So collision means what? The suppose M is the organic molecule or analyte which in a gas phase. Okay, remember that analyte must be in a gas phase. It should not be in a solid or liquid phase. Okay, so that's why we require temperature. So here we can set the temperature to keep the analyte in a gas phase. Then, then it will work. Otherwise, it will not work. So M is the some component or analyte in the gas phase, and this electron will collide, and there will be a reaction like this one. So electron from the molecule analyte will be taken by the electron, and there will be formation of the two electrons. So analyte will donate one electron and will get the positive charge. So here you can see that this molecule or analyte in gaseous phase converted into the M plus. Plus is the charge on the analyte, which is also in a gas phase, and there is formation of the two electrons. Now these two electrons will be accelerated towards the anode to measure the current. How much electrons are produced here and will be measured for the analysis. So this is the collision. This reaction takes place here. So after formation of the ion, so here you can see that there is formation of M plus means molecular ion. Okay, so just only one electron is removed from the ion. That's why it's called as molecular ion. Remember this word in mass spectroscopy. You can see that when one electron is removed, it is called mass spectrometer. Okay, so when there is a formation of ion or molecular ion, it undergo fragmentation. So these words are known to you. Okay, so there is a formation of fragmentation. Fragmentation what? Means breaking of the molecule ion into different parts. Okay, and this molecular ion is rarely observed. Okay, what is the meaning of molecular ion is rarely observed means what? If it is stable, then there will be a peak in the mass spectra. Huh? If it is not stable, you cannot see, or there will be a small peak for the molecular ion, which is hard to depict, hard to detect. Okay, so that's why it is called the molecular ion is rarely observed, and the fragment ions are easily detected, and ions are directed to the mass angle. So always remember, peak for the molecular ion is very small as compared to the peak for the fragments, because these molecular ions are very less stable. Okay. Now, one important point while using ionization or EM. Suppose your energy of electron is very less. In this case, we can see that here in bracket we have written 70 electron volt. Suppose this energy is very less, is less than 15 electron volt. So what will happen? Next slide will discuss this point. Now here you can see that there are two spectra of the mass for the same compound. Name of the compound is benzophenone. The first spectra is for same compound which works at electrons having 70 electron volt energy, while the second spectra is taken with the electron having only 14 electron volt energy. So you can clearly see difference in the IR spectra. Okay, so In first case, because of high energy, this spectra is taken at 70 electron volt. Okay, so you can see the red line, which is for the molecular ion. Means only one electron is taken from the molecule. That's why it is called molecular ion, and it has very less intensity because at higher energy, this molecular ion is less stable. So that's why you are getting small peak. But when electron has less energy, you can see that this molecular ion has great intensity as compared to the first one because the energy of electron is very low. So in this case, this molecular ion is more stable as compared to the first one. But this part you can see that there are number of peaks. In this case, there is only one peak. Means what happened? You need more energy to do the fragmentation of the molecular ion. And this is the important in the mass spectroscopy. Okay. Otherwise, you cannot detect or you cannot analyze the which compound is present in the given sample. So when you have enough energy to fragment this molecular ion, then you can observe the peaks in the mass spectra. If electron doesn't have sufficient energy or enough energy, you will get only molecular ion peak along with the one or two fragment peak. Okay, so remember that the energy of electron must be sufficient to give the fragmentation of the molecular ion. Now let's see one video on this electron impact ionization, so you will understand how it works. So electron ionization in mass spectrometry. So this is the ionization chamber. This is the filament, which is red color. Now remember this yellow dot is the neutral molecule, plus pink is the positive ion, and orange is the electron. From this side, inlet, sample inlet means samples will come inside from this, like this sample will come. Now this filament, and this filament is connected to the supply, electrical supply, so it will be heated. This filament is either rhenium or tungsten. Okay. Now this will produce the electron and will come and will get collide with the molecules. So you can see that after collision, there is a formation of the positive ion from the neutral molecule, and this electron they move to the trap electron. So this is the positive ion. The electron will attract to this end, and current will be measured. Now this is the positive ion. We have to move this positive ion towards the mass analyzer. So this is the mass analyzer is connected at this end. So what we are doing? Just we are passing the positive current supply. Okay. So this positive and this positive will repel. So automatically this positive ion will move from this place to the analyzer. So this way sample ion pass into the molecule. So this is the compound, just only one electron is removed, so it will form the positive ion, and it is called molecular ion. Remember that when one electron is removed, it is called molecular ion. So now let's see the fragmentation. So what is meant by fragmentation? So this is the pentane compound. So when it is electron collide, so there is a formation of the molecular ion. So this is the first step. So only one electron is removed. After electron having sufficient energy, these molecules get fragmented into different types. There is number of possibility where fragmentation can take place. So you get the various fragmentation after formation of the molecular ion. In this way, this ionization chamber works. Okay. So this is the end of the ionization chamber. Okay. Now turn your mic and camera.
कसं करतो तो करतो.
Okay, so far we have seen detector, interference and ionization, electron impact ionization. Anybody have any doubts? Hmm? Any doubt from boy side, girl side?
No.
No.
Sure. Okay, now I will ask one question to you. You have to find out the answer. Why in MS why high vacuum is used? Okay, why high vacuum or low pressure is used in the MS? You have to find out the you have to find the answer for these questions. Okay, just do search in Google, you will get the answer. Okay, now we will stop here and next lecture we will see the second analyzer and mass analyzer. Okay,
Okay, sir.
if you have any doubts, frankly ask, or you can call me or give message. I will reply to your question. Okay,
Okay.
okay,
Okay, sir.
okay. Then see you next lecture.